The first sign came from orbiting eyes in space, September 12, 2025. The Swan instrument, part of the Solar and Heliospheric Observatory, detected a sudden blaze, a new object, unmistakable and massive. Its tail stretched nearly 2.5 degrees across the sky, from the apparent width of the full moon, a scale that defies comparison with modern comet discoveries. Magnitude 7.4, bright enough for amateur telescopes, even binoculars. By September 13th, the International Astronomical Union confirmed the discovery, C/2025 R2, dubbed Swan for the instrument that first saw it. Excitement swept the astronomical community, but alongside it, disbelief. This wasn't just another icy visitor. Swan was commanding, bold, bright, and the numbers told a story of scale and energy that didn't match any ordinary comet. Astronomers around the world noticed something extraordinary. A colossal object was streaking inward from the depths of space. Its tail stretched 5 times the width of a full moon, far surpassing anything observed since Oumuamua. Within hours, a second object was confirmed, racing toward the sun just weeks apart from the first, yet arriving from nearly opposite corners of the sky. The statistical odds of such a double entry were astronomically low. The official explanation called them twin comets. Yet the emerging patterns and behaviors hinted at something far more complex. This was not merely a random cosmic coincidence. The geometry, timing, and energy involved suggested a scenario that invited deeper questions. The first detection came from the SWAN instrument aboard the Solar and Heliospheric Observatory. Its sensors caught a massive, bright object blazing through the solar system, almost impossible to miss. The tail of this visitor, later designated C/2025 R2 or Swan, stretched nearly 2.5 degrees across the sky, roughly 5 times the width of the full moon. With a magnitude of 7.4, it was visible not only to professional observatories, but even to amateur astronomers with modest telescopes or binoculars. Within days, the astronomical community was ablaze with observations. Images poured in from backyard observatories, particularly in Australia, where photographers captured streaks of light so long they spilled beyond the frame. By September 13th, the International Astronomical Union officially confirmed Swan's discovery. Scientists and amateurs alike shared measurements, debated its brightness, and tracked the rapidly growing tail slicing across Virgo. Swan was unlike any comet discovered in recent decades. Most modern comets are faint, requiring powerful telescopes to detect. Swan, in contrast, was brilliant, commanding, and impossible to ignore. Its size, brightness, and energy output set it apart, drawing both excitement and a sense of disbelief. But Swan was not alone. Just days earlier, 3I/Atlas had entered the inner solar system as well, approaching from a completely different sector of the sky. Swan came from Aquarius, Atlas from Sagittarius. Their orbital paths are separated by more than a quarter of the celestial sphere, yet their perihelion, the closest point to the Sun, would occur within 3 days of each other. Atlas would reach perihelion on October 17th, roughly 203 million kilometers from the Sun, while Swan would follow on October 20th, at about 150 million kilometers. The geometry alone was staggering. Swan's orbital plane is inclined more than 60 degrees relative to the ecliptic, Atlas nearly perpendicular. Astronomers accustomed to long-period comets rarely see perihelia clustered in such a tight window. The combination of timing, orbital paths, and solar proximity made chance an unlikely explanation. Adding to the intrigue, both objects would traverse this region during a natural observational blind spot. From October 8th to 18th, the sun's glare renders ground-based telescopes largely ineffective. The critical moments, closest solar approach, potential interaction, and observable anomalies, would occur in near-total darkness for official observers. The blackout creates a corridor of space and time where independent observation becomes crucial. Atlas immediately drew attention, not for its brightness, but for its composition. Spectrographic analysis revealed a body dominated by nickel with minimal iron, a profile that contradicts typical cometary chemistry. Carbon dioxide emissions vastly exceeded water, with CO2 lines 5 times stronger than H2O water. Worldwide observers tracked stepwise accelerations in the tail, 3 distinct pulses, each spaced roughly 2 weeks apart, each coinciding with abrupt changes in brightness and color. These delta pulses, unlike the smooth, solar-driven outgassing expected from comets, suggested a controlled energy source within Atlas, energy that undoubtedly influences our frequencies here on the Earth. Independent verification confirmed the phenomenon across multiple observatories, from the Abaro Tracker Network in Europe to distributed telescope arrays around the world. If these accelerations are real, the implied energy output approaches 10 gigawatts, the equivalent of 10 large nuclear power plants. Conventional cometary physics cannot account for such levels of active propulsion. These advanced discoveries reveal that energy sources can be pushed to higher productions. Nuclear likely because they are safely adapted. SWAN, in contrast, presented as a slow, steady juggernaut. Its tail already surpassed record lengths, and early photometric estimates suggested a core output exceeding 10,000 gigawatts. Reflectance data showed metallic signatures, nickel, possibly blended with cobalt, consistent with materials chosen for strength and resistance. Observers noted a silvery halo around the nucleus, fluctuating with the solar wind, reminiscent of a plasma envelope capable of deflecting charged particles. Swan moves like a cosmic fortress. Micro-thrust pulses subtly adjust its trajectory. The rhythmic changes in tail direction and brightness hint at an internal control mechanism, far beyond what random outgassing could achieve. Its orbit, a staggering 22,554-year cycle, reaches back to the last ice age. This is not just an isolated incident. If engineered, it has been following a preset course for longer than recorded human history, arriving now alongside Atlas during the sun's observational blackout. The synchronized arrival of Swan and Atlas inspired multiple theories. One scenario imagines a scheduled solar flyby for recharging, data transfer, or systems audits, using the sun as a power node. Another theory suggests rendezvous or intervention. One object could be correcting, recovering, or interacting with the other. A third framework considers a sequence of escalating probes from Oumuamua to Atlas to Swan, possibly monitoring Earth's radio transmissions and environmental signals. In all cases, the sun is not just a backdrop, but an active participant in the mission. An energy source, a beacon, a rendezvous point. Swan's orbit also evokes mythic resonance. Its last passage coincides with the end of the last ice age, around 20,000 BCE. Glaciers were retreating, early human societies were emerging, and monumental constructions such as Göbekli Tepe were taking shape in southeastern Turkey. Some researchers suggest that the site's carved pillars, featuring animals and abstract symbols, may represent celestial observations, potentially even cyclical cometary passages. While speculative, the timing aligns intriguingly with Swan's orbital period, inviting connections between cosmic events and the earliest human awareness of the heavens. During the solar blackout, official observatories were constrained. Radar imaging, high-resolution photography, and even raw data access were restricted. Yet amateur astronomers rose to the challenge. Networks of backyard observers, pooled observations, repurposed radio telescopes, and even adapted weather satellites to track the hidden visitors. In this vacuum of official oversight, the search became grassroots. Anyone with a telescope, a dish, or access to open-source tracking software could contribute. Two anomalous objects entered the inner solar system together. They defy expectation. The blackout is ending, signals return, and with them, the secrets of the twin anomalies. As Swan and Atlas re-emerge from behind the sun, the first signals will likely come not from government labs, but from the dedication of these independent observers. The story of these twin anomalies is not simply about orbits and magnitudes. It is a tale of cosmic precision, mysterious energy, and the faint echoes of humanity's earliest encounters with the sky. Two rare objects entered the inner solar system together, defying statistical probability and challenging our understanding of long-period comets. Are they random visitors, probes with a mission, or echoes of cosmic cycles recorded long before humanity looked skyward? The answers remain uncertain, but the pursuit of discovery continues, drawing humanity into a journey across space, time, and the unknown. In the end, standing at the frontier of knowledge, we realize that curiosity is our compass, and wonder is our guide. The cosmos stretches on, eternal and inscrutable, and we are privileged to be its witnesses. So many portals and options to embark on a timeless path. Each revelation from the James Webb Space Telescope is a reminder. The universe is alive, expanding, contracting, mysterious, and waiting to be explored, even if not necessarily completely understood. And as we continue this journey, one thing is certain: we have only just begun to scratch the surface of the infinite voyage. Join me in this adventure